Okay, sorry about that. Okay. So, and then we'll do some practice problems, and we will have a question and answer section following. All right, and feel free, this is a live question and answer session. If you want to jump in at any time, I'm happy to answer any questions you might have. And we have some opportunity if you want to drop some practice problems in the chat. That would be fine, since that's what we're here for. All right, so let's review our first rule. That's the power function rule. This is probably the first rule you learned when you were first learning derivatives. I just want to make sure everyone has a good handle on that. Before we begin, so basically, to do a power function, to do a power rule of the form x to the n, to derive that, you're going to bring the power out in front and then raise x to the n minus 1 power. So, for example, if we have this 4x cubed, if you're out there in the chat, since I assume everyone know that, just make sure you're out there by dropping what you think the answer to that would be. If you can see me. Yeah, that's exactly right, Emma. So you're going to move that 3 out in front, and you're going to get 12x squared. So that's really kind of a simple one, just making sure you knew that. Moving on. Now this is the first of our two-step functions. And so what we're going to do for this one is when you add and subtract functions, all that really matters is you take each piece and add and subtract them together. So here we would have 8x plus 5. Just because we take this part, and then the derivative of this, and then the derivative of this, and then the derivative of this, just using the power rule. And you can remember that the derivative of a constant is 0. So moving on to trig functions briefly. Here is what the derivatives of trig functions look like. So you can see those are the 6 basic trig functions, and then these are their derivatives. Once again, if you're a 5able Plus member, at the end of my last session, Derivative Practice Streams 1, you can see how these all work, and it's kind of interesting how that might work. So just to make sure, so what would the derivative of this one be? Just to see if you have a mastery on those. Yep, right here on the ball. Again, so you can see it just becomes 2 cosine x. And remember this, constants just stay out in front as multipliers. They don't, you don't have to worry about those as derivatives. All right, so next kind of group of rules that we're reviewing, and once again, if this is going a little fast, you can check my last stream where I go over some of these exact problems in more detail. So for the product rule is where you first start to have to do some sort of algorithm. So the kind of word way to remember this one is it's the first times the derivative of the second times the derivative of the first. And remember, because addition is commutative, it doesn't really matter which one you do this, so in order can kind of get fudged around a bit. So for this one, we're going to take the first and multiply it by the derivative of that one. And to that, we're going to add the second times the derivative of this, simple power rule. And if you wanted to clean that up, you would probably move that out front, just because normally you're going to put power functions before trig functions. Once again, that's just kind of a convention that you do. It's really kind of silly that you do it that way, but you don't even really have to do it most of the time. On the AP exam, they unless it says simplified form, you can leave it kind of a mess because AP exam graders do actually have some sort of sympathy. They are not just robots; they are human beings, and they do. Oh, hi, Tam. Thanks for stopping by. It's they will look and see if you've got that in some sort of crazy radical or quotient form. They won't really care as long as you've got the answer. Then once again, as long as it doesn't say that it has to be expressly simplified. All right, so now on to the quotient rule, and this one is, as you can see, it's a kind of a behemoth. So the quotient rule again, once again, for those of you who haven't learned, is the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Now that's I know that it seems it's a bit complicated, but once you do it, you'll just kind of get the hang of it. And once again, because division and subtraction aren't commutative, as you probably learned in elementary school. This means that it does matter which order. On this one, you can switch these two terms around, but for this one, it actually does matter. So which order you get these in. So let's just quick do this one. So if we've got our g, which will be 2x, and our f, which will be this 3x squared plus 1. You can see that we'll have the bottom times the derivative of the top. Once again, simple power function minus the bottom times the derivative of, or the bottom, wow, sorry, tripping over my words here, times the top, which is green, times the derivative of the bottom, which is 2 over the bottom squared. And once again, you can simplify that into what would it be, 12x squared minus 6x squared plus 2. And another thing is, throughout the stream, I like to kind of chuck in things that were kind of my struggles during, reviewing for the exam and taking the AP exam. One of those for me is you find that one of the first things that you forget under pressure is simple algebra. And don't worry if you've experienced that on your test before. You're not alone. I've got a lot of people who, joke that we can't do arithmetic without a calculator anymore. And that's completely fine. So just remember, on the bottom square, don't just square the power. It is indeed this 2x quantity squared is 4x squared. Just a little tip: don't always remember that. Don't forget that in a moment of when you're under stress. Always make sure remember where your parentheses are, especially since, as you can see, your handwriting often gets kind of messed up under stress. So always make sure that you've got a clean head and make sure you've got all your algebra right, since that's something you've probably been doing by years if you're taking calculus. All right, enough of that. Now moving on to the chain rule. Now you'll use the chain rule when you have two functions inside of each other, or as the name suggests, chained together. So what you're going to do here is that the way my teacher taught me is that you're going to want to work from the outside in. So what that means is if you're taking the derivative of f of g of x, you're going to want to take the derivative of f with g as x in the middle, and then you're going to multiply it by g prime. And you'd keep using that sort of algorithm if you have three functions. So if you've got f of g of h, you do f prime of g of h times g prime of h times h prime. And the chain rule is one of those sneaky ones. It kind of sneaks up on you. Like, for example, here we can see that we've got sine squared x, and you're like, well, that doesn't really look like two functions inside of each other. But if you break it down, you might remember that sine squared of x is just the mathematical shorthand way of writing sine x quantity squared. And so there you can clearly see we've got this sine x inside of our squared inside of our power function. So then we have to chain rule that so this function would be an application of the chain rule. So how this might look is you'll just do this like you'll derive the outside with normal, like normal, and you'll see it'll be 2 sine x, and you're like, well, why don't we derive sine x? That's because, as I mentioned earlier, that g of x, so your g of x function is sine x, and your f of x function is x squared. So just let the sine x just kind of sit there while you derive the outside. Sort of like I almost imagine if you've got 2 spheres that you need to twist to unlock inside of each other, you unlock the out sphere, but you don't do anything to the middle in it. Or when you're taking apart one of those Russian nesting dolls, you take apart the outside without doing anything to the inside. You can't just rip it all apart. So you've got to do it a layer at a time. All right, now so those are our review of some rules. And now let's look at some new rules. So these are some new one-step derivatives that we haven't covered yet here on our review streams. And these 4 primarily have to do with logarithms and exponential functions. So we'll begin with the easiest. The derivative of e to the x is e to the x. Not much to it. This is because you'll find that in Calc, if you look at these derivatives, the pattern will follow that the natural log sort of is at the core of all of these derivatives. And so this one, this is kind of the core of these 4, so it makes sense that, the derivative of e to the x is just really the simple e to the x. All right, so our next rule is a slightly different one. If we've got just any exponential function, b to the x, the derivative of that is b to the x times the natural log of b. So what that'll look like is that the derivative of that. So we'll see that we just rewrite that function like e to the x, but because it isn't e to the x, we've got to kind of make it more like e to the x. We multiply it by the natural logarithm of 2. And just making sure you remember from previous courses, ln of x is of course equal. So that's why. So that's how that works. And this fact and that becomes actually a really interesting way in which this next rule, the derivative for any logarithm, is calculated. And so you can see I have the derivative of the common log above the derivative of the natural log. And that seems kind of logical because the natural log is the special version, so you'd think it would be special. But when we're dealing with derivatives, it's actually the other way around, which is really kind of interesting. So I'm actually going to skip that one and look at this derivative. So the derivative of the natural log is just the natural log of x is just 1 over x. And that's, once again, that's kind of a simple rule. You'll notice these two, e to the x and ln of x, these are kind of deceptively simple, and there's a reason for that. I won't go into it now since this is just more of a practice stream, but you can, if you use the definition of the natural log, you can see why those are. Anyway, I digress. So going back to this one, you can see this is kind of complicated, and you can see it kind of follows some of these other patterns, but we're going to look at why this is that way. So if we've got the log base b of x, you might know that by the change of base rule of logarithms can apply here, and if we change it to base e, so log base e, using the change of base rule, we have log base e of x over log base e of b. That's known as the change of base rule. So we're going to change these to some base e. So now when we derive that, we can do the quotient rule. Sorry, just a sec. There we go. So if we do the quotient rule for that, we'll have the derivative of the. So if you do the quotient, sorry, I lost my train of thought there. So this you can, if we derive that, we'll just simply get 1 over x times the natural log of b. And so that's kind of how this comes out of this. It comes out of here. So don't worry. If you forget this complicated rule, you can just remember that log base b of x is equal to the natural log of x over the natural log of b. And then if you derive this using the quotient rule, you'll get this, because remember, the natural log of b will just be a number. So when you do the quotient rule, that'll become 0. And so the quotient rule becomes much simpler. That's another kind of top tip for if you are doing derivatives. Remember that the natural log, or remember that you always want things in the quotient rule to equal 0 as often as possible. So I think actually I'm going to add a couple more rules. They're not in my examples, but just to kind of round out the most common examples that you're going to use, the most common rules that you're going to use. The inverse trig functions are another set of rules that are really oftenly used in AP Calculus. So, and those are arcsine of x, arc cosine of x, and arc tangent of x. Now you can go about and you can go through and do the trig derivatives for these using trig, but just suffice it to say the derivative of arcsine of x is 1 over the square root of 1 minus x squared. The derivative of arc cosine is negative 1 over the square root of 1 minus x squared. And the arctangent of x is just 1 over 1 plus x squared. And like I said, in class you might have done the trig derivatives of these, found the derivatives using trig. You can see that they're basically just applications of the Pythagorean theorem here. But so those are the 3 inverse trig derivatives that you might see used. Like I said, I don't have any practice problems prepared for those, but we can go over those later if you guys have any practice problems that you want to do that use any of those. All right, so now we're through kind of the introductory part where we review all these rules. So now we can go over and we can do some practice problems that I've prepared that use a combination of these rules, both the rules for combining functions, the chain rule, power rules, exponentials and logarithmics, and the trig derivatives. So this first practice problem. We can see that we've got these 4 individual functions, each joined by addition, which means that we're going to take the derivatives of these and add them all together. So let's do this piece by piece. So the derivative of 5 to the x is going to be, that's like we just learned, that's an exponential function. So it's going to be just that same thing repeated, but with the additional ln natural logarithm of 5. Then we've got 3 power functions here. Well, this one, we'll get to this term later. But our next part, we'll just add the derivative of this. So we'll multiply that and raise it to 1 less power, 8x. and to that we'll add the derivative of this 6x, so that just becomes 6. Now, intentionally, I've made this a little bit complicated. You can see we've got this big complicated fraction with 152.354 and pi, but the thing you have to remember is that it's a constant. A number is a number, and the derivative of any number is 0, because if you remember, that is really just that constant whatever times x to the 0. So we multiply that and it becomes 0, and it just all cancels out. So that's that problem. Now this next problem, you can see we've got the sine of x over the common log of x. So in the chat, what do you think the basic structure that we'll be using, how are these two functions combined, in other words? Right, so you can see that this is going to be an application of the quotient rule. So let's get ready for that. And so let's do this. So we're going to have the bottom times the derivative of the top minus the top times the derivative of the bottom. Now you can see we just have log x, and if we go over to our and if we look at our rules, we remember that we need this base. So this log x is what I think it's termed the common log. So this basically means it's a shorthand for writing log base 10. And just a brief kind of disclaimer, this is what the log button on your calculator does. So you have to do a separate command for log base b. I think on TIs it's in the math. If you punch math and then you can scroll down, you can see log base b. Just a quick shortcut so that you don't have to do the change of base rule for every logarithm, although that's what your teachers may have told you. It saves a ton of time to just do the shortcut way. All right, so we're going to multiply this by the top times the derivative of the bottom, which is just going to be, oh my, hang on, which is just going to be using this rule. It's going to be 1 over x, which is just going to be x, times the natural logarithm of the base. And this will be over logarithm x squared. And just for fun, we're going to simplify this. So it would be log x cosine x minus 1 over sine x, or x sine x ln 10 over log x squared. And if you really want to simplify this down, and let's actually keep simplifying, decided. So we can split this, subtract from that 1 over x sine x ln 10 over log x squared. And then if we see what this will do, this will cancel. And then when we multiply by the inverse of that, it'll just become 1 over that. So that's that problem. So moving on to our next problem, we can see we have ln of x sine x, and this will be a product rule. So what we're going to have is we're going to have the first times the derivative of the second, and to that we'll add the second times the derivative of the first. And if we just simplify that, we'll have that. So that's a pretty simple application of the product rule, and adding in this new wrinkle of our logarithmic functions. All right, so let's move on to our, oh, let me see, you've got a question. Yes, sine of x is not in the denominator, wherever. All right, glad you figured that one out yourself. All right, so let's move on to our next group of problems, and some of these are a little bit more complicated. So in this first one, what do you see as kind of being, there are two big things that we're going to have to do in problem number one up here, and what do you think those two are? Or two types that we're going to have to combine functions using. Right, so we're going to have to do the chain and the quotient rule. So if we look, we always want to start, even with the chain rule, like the chain rule, with derivatives in general, you got to work from the macro level to the micro level. So you can see that the whole thing is encased in a quotient rule, which means we're going to have to do the quotient rule first. So we're going to have the bottom times the derivative of the top. Now the derivative of this, you can see we've got a log base 10 inside of a natural logarithm, or a log base e. And so what we're going to do here is we're going to take the derivative of the outside with that log of x, or rather, well, you can see oh my, there we go. So what we're going to have is 2 to the x times 1 over the natural logarithm of x. Because you can see we take the derivative of the natural logarithm with that log of x still inside, and we're going to multiply it by the derivative of the natural logarithm, which is 1 over x ln 10. And then from that, we're going to subtract the top times the derivative of the bottom, which will just be 2 to the x ln 2 all over the bottom squared. So if we're simplifying this, we're going to have 2 to the x over, multiply this together, ln 10 x log x. That's still a fraction. I need to scoot my canvas over. Minus this mess, ln of log x times 2 to the x ln 2 all over the bottom squared, and 2x to the 2 would become 4 to the 2x, I believe. Don't quote me on that. No, yeah, it would become 4 to the 2x. Sorry for the doubt there. All right. So let me erase all of these annotations. Now moving on to this next problem. Now you can see we can simplify this, but I would like to do this one kind of as it's written here. Obviously, another AP exam tip. If you're going to do problems, if you're going to have to do derivatives, you should always simplify them as much as possible before you derive them, as it'll just save a lot of time for you later. But here, in order to practice our rules, we're going to do this one as an application of the chain rule. And it works out the same as if you simplify it. So first, our big function is a power rule. So we're going to multiply that, and we're going to multiply this by the derivative of the inside, which is just e to the x. All right. So for our next problem here, you can see we've got three rules all chained together, or 3 rules all added together. And so what we're going to do here is we're going to take the derivative of each one individually and then add them all together. So the derivative of log base 2, this is just another common logarithm like we've done in the past. And what we're going to do is we are going to, that is of course of 1 over x times the natural logarithm of the base, which is 2. And then to that, we're going to add these two. Now, radicals are another thing that we want to simplify. And radicals can be expressed as fractional powers. And so basically how that works is if we have the 8th root of b to the x, or of x to the b, that is equivalent to x to the b over a. And if that's kind of difficult to remember, you can remember that by remembering that the square root of x is x to the 1/2, so that you can kind of extrapolate how that works. So, knowing that this is x to the 1/2, we just treat it like any other power rule. And we have 1/2 times x to the negative 1/2. And then to that, we're going to add the derivative of this. And once again, this is another radical, or a power, hiding as a radical. So that's going to be x to the 1/3. And so what we're going to do here is we are going to treat this once again like any other power. We're going to 13x to the negative 2/3. And so now this can be done as a little bit of simplifying. So we have 1 over x ln 2. This, we remember that negative powers are really fractions. So we've got 1 over 2x to the 1/2 plus 1 over 3x to the 2/3. And so simplifying this again, we have 1 over x ln 2, and then we can change these back into radical form. So it's 1 over 2 root x plus 1 over 3 times the square root of x squared, or of x cubed rather. Sorry, still working out this new interface. I've switched. It's a lot better than the old one. It actually allows me to draw on without having to show you Microsoft PowerPoint. But there's still some quirks that need to be ironed out. All right, so moving on to my final practice problem of the night, tangent x times sine to the 4th of x. So this once again, so this is another combination of a chain and a product rule. So if we rewrite this to make that more apparent, we've got tan x times sine x to the 4th power. So we're going to have the first times the derivative of the second. So keep that, remember, keep this intact, times the derivative of that. And to that, we're going to add, well, come back here, the second times the derivative of tangent, which, if you recall from our trig identities, is secant squared of x. So simplifying this a little bit, we get tan x, and remember that this, we're going to change that back into this notation, plus sine to the 4th x secant squared x, and we can actually do a little bit even more simplifying, because we can see that we've got sine cubed x in every term. Plus sine x secant squared x. All right, so that is that problem. And so now we have we've got about 20 minutes left. If there's anyone out there who has their own practice problem that they would like to see done, there's a problem that they're struggling with that they would like help with, as long as you think that it would be within, reasonable, as long as you think it would be, of course, okay for you to be helped with it. You can go ahead and drop it in the chat if you've got any sort of problems. Otherwise, we can just keep doing some more that I'll kind of come up with on the spot, since those are all the ones I have those are all the ones I have prepared. All right, I don't see anything coming in. That's okay. Just a second while I finish clearing all of these off. So now that we've kind of gone through all of these, just a fair word of warning. This on the AP, if your teacher hasn't taught you about the format of the AP exam, or if you're not in a normal AP calculus class, and so you're just kind of studying for the AP exam on your own, first, kudos to you. The AP calculus exam is even more tough, I would say, than a normal calculus exam. And so it's really difficult. And so AP exams, as you know if you've taken any other AP classes, are much more elaborate in format than than just a normal classroom exam. And so part of that is that you don't just have simple do this math problem as much. I mean, on the multiple choice questions, you'll get some of that, but in many ways, it's a lot simpler. Or it's a lot more complicated, rather, because you're not just doing things algorithmically, especially on the free response questions. So what you're going to have is you're often going to have it where you have multiple where you won't just have a simple do this derivative. It'll be incorporated into all the concept you've learned in this course, so it won't just be organized on a simple kind of unit by unit basis. So oftentimes this derivative will be part of like the integral, which you'll learn about later, or you'll have to do it as part of a limit problem. And so just a really kind of important tip that I have is getting these derivative rules down pat, so it just can become kind of the easy part of a problem. I'm still not seeing any practice problems, so just a second, I'm gonna go dark while I take a short breather, and then I'll be back in like 30 seconds with some more practice problems. So sorry for the brief intermission, but I'll be right back in like 30 seconds. All right, sorry about that, I'm back. So I'm still not seeing any practice problems or any problems that you want to do in the chat. So what we're going to do is actually, just to get some more practice, I'm going to run through something I did the other night when I had a similar situation, and where you're going to look at just get more practice with these simple derivatives, and take a fun little exploration into how these three problems were done. Sorry, I know I'm rerunning content if you were here the other Saturday about a month ago, but I was kind of expecting we might have some practice problems. So let's take a look at how we might do these. And I need to turn my screen sharing back on. Given what we're going to say is that given these two rules, how might we find these four rules? And this is kind of an interesting little exercise and also a nice thing to do since sometimes you really don't have these other four memorized, and it's easy to get them confused. So this is how you might check yourself. So if you remember that sine is cosine and cosine is negative sine, because for perfectionists like me, getting a C is negative. That's how I kind of remember that. Let's look at how we find these four derivatives. So for tangent x, we're going to have sine x over cosine x. And what that will be equivalent to is that you can see we're just going to do a simple product rule here again, or a simple quotient rule here again. So what we're going to do is we're going to take the top, or the bottom, times the derivative of the top, minus the top, times the derivative of the bottom, over the bottom squared. And so now we could use some simple algebra and trig to simplify this. So what we're going to get is we're going to get negative cosine squared x minus sine squared x over cosine x squared. Well, and this is where you kind of need to use your knowledge of a little bit of trig. And something you might notice that this looks kind of suspiciously familiar, and you'll notice it might look even more familiar if we pull a negative out. We've got sine squared x plus cosine squared x over cosine x squared. And if there's anybody in the chat who here knows what this little part, sine squared x plus cosine squared x, is equal to, maybe if they remember from an algebra 2 or geometry class, what that identity is. All right, I'm not seeing anything. So you might remember that this is a trig identity that's equal to 1. This is simply a application of the Pythagorean theorem. So what we're going to have is that becomes negative 1 over cosine squared x, and using the additional 3 trig functions in equal to sine, cosine, and tangent, you can see that that's equal to negative secant squared x. All right, so that's how you derive tangent x, the derivative of tangent x. So now let's move on. Whoop. Sorry. Oh, it's not deleting for some reason. I'm going to have to do this way then. All right. So for our next derivative, we can see we've got secant squared, which is, of course, just, now it works, 1 over cosine x. So this is another application of a simple quotient rule. And so what we're going to do is we're going to take the bottom multiplied by the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Now, if we simplify this, we have sine x over cosine squared x. And you're thinking, well, that doesn't look a lot like secant times tangent. But if we simplify this to what it is, you can see that we've got sine x over cosine x times cosine x, which is equivalent, of course, to tangent x times 1 over cosine x, which is, again, equivalent to secant x tangent x. All right, so that's how you find the derivative of secant. Our next rule is cosecant. So what we have is and you might know that cosecant is, of course, equivalent to 1 over sine. And that's another thing to remember. Another thing to not get confused under the pressure of an AP exam that sine x are that sine and cosine, it's backwards for cosecant and secant. So remember that sine, 1 over sine is cosecant, and 1 over cosine is secant. All right, so we're going to do a similar product, our quotient rule, like we had for like we did for secant. So it's going to be the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. And so simplifying this again, we're going to see that we get negative cosine x over sine squared x. So once again, it doesn't look a whole lot like this, but you can maybe see where this is going. If we simplify this, we get negative cosine x over sine x times sine x. Just 1 second. All right, so we can see that that's equal to negative cosine x over sine x times 1 over sine x. And simplifying that again, cosine over sine is equal to 1 over tangent, or cotangent, times 1 over secant, which is cosecant. All right, so moving on to our final. Notice we've got some new viewers. If you've got any problems or derivatives that you would like help with, feel free to drop that in the chat, and I can give you a hand. And moving on to our final derivative for these trig functions, we have cotangent, which is of course equal to cosine x over sine x. And this will kind of be the opposite of our tangent derivative, but just to tease this out, or not rather tease this, but just to kind of figure this out, we have the bottom times the derivative of the top minus the top times the derivative of the bottom all over that bottom squared. So what we're going to have is we're going to have negative sine squared x minus cosine squared x. And once again, that'll be 1. So it'll become negative 1 over sine squared x, which is equal to negative cosecant squared x. All right. So once again, I'm not seeing any sample problems in the chat. So sorry, gotta quick check something. All right. So what we're going to have here is so that's all of my trig derivative examples. So let's go over here, and I'm gonna just for fun make up, or rather, hang on, so let's look a little bit more actually, since we've got about 7 more minutes. Let's take a look at our at those arcsine, cosine, and arctangent again. So let's do something like this. So this is, again, a quotient rule with a product rule in the numerator. And so what we're going to have is over the bottom square. So let's just put that all over the bottom squared first, and then let's move on to doing the numerator of this derivative. So we're going to have the bottom times the derivative of the top, which is going to be a product rule, or it's going to be a product rule. So we're going to have the derivative of this first function, which is 1 over the square root of 1 minus x squared, times the second function plus arcsin x times cosine x. We're still all over this, minus the top times the derivative of the bottom, which is going to be negative sine x. So that's a bit of a monster, so simplifying that a little bit. Simplifying this first bit, we get cosine x over 1 over root 1 minus x squared times sine x plus arc sine x cosine x. So simplifying that first half of that term again, we get cosine x, can pull that out, times 1 over the square root of 1 minus x squared times sine, we'll put that on top there, sine x plus arc sine x minus this second part, which is, again, so we get sine squared x, arc sine x over cosine squared x. If we wanted to, we could simplify this even more, but we don't really, that's not really the point. Like I've repeated throughout this stream, the important part here is that you have all of your, is that you understand that you don't have to do only as much simplification as is necessary. I'm just doing simplification because it's good to do your algebra practice, but if you don't have if you don't do simplification, then that's perfectly okay. Because on multiple choice, you should just simplify it as much as you need to. So as much as you need to get the answer. So for example, if you just need to get it as simplified as you can in order to see if you can see which choice it is. Now be careful. They're very good at a typical AP multiple choice question with 4 answers, or with 4 or 5 answers. This works for any. I took the AP US History exam. I've taken the AP Spanish exam. All of them work kind of similarly to this. So if you've got 5 answers, you'll have, what it'll normally look like is you'll have you'll have 3 plausibles, a good answer, and then the correct answer. And then these two. So this is what your typical AP multiple choice question will look like. Whether this is mathematics, history, like I said, or otherwise. You'll have 5 answers. All of them seem right. So if you're doing a history question, they'll all have kind of terms or buzzwords, if you like, around the theme of the question. And so what this will mean is that they'll all be plausible, but 2 of them, you should always try to strike out ones that don't quite make sense in the context of the question. So for example, they might They might just contain the wrong greater rule form. They might use an incorrect definition, like they might use for example, there are two definitions of the limit. There's the definition of the limit as x approaches infinity, and there's the definition of the limit as h approaches 0. They might use the wrong definition of that, so they'll be out of context. Rule those out immediately. Then you'll be left with one kind of plausible answer, one good answer, and one correct answer. Now, those good and correct answers, those two will be very close, but one of them will be right. So what you need to do is do enough that you don't just accidentally go for the good answer. Those will be the trick answers, the kind of red herring answer. So go derive as much as you need, but don't derive, but don't do any more don't do any more math than you have to if you feel like you're behind pace. And if you're not behind pace, then take a deep breath and think through it more carefully. I had another test-taking strategy thing in mind for me. I'm a little bit flustered here that I've run out of material. So once again, if you have any questions, drop them in. I'm more than happy to answer things. Right, I think that's about all I have. I'm just thinking if there's any last things for these. And so I've said, once again, remember, don't get things confused. Take your time, make sure your derivatives are down pat. Another kind of thing is if you forget something, the reason I just did all of these example derivatives is because if you don't remember something, figure it out if you can. Because especially on the FRQs, partial credit on the free response questions is your best friend. So make sure you can get as much done as you can. So whether that means taking some time to quick scribble something out and deriving a formula for something that you know kind of the basic form. So if you know those, if you know your core derivatives, that's fine. If there's another one and you have time, always kind of scribble that out. And my final kind of test-taking strategy that I'm going to leave you with is approach things strategically for how you best do them. If you're kind of one of those person who looks at an exam and kind of goes from easy to hard problems or hard to easy problems, do that. Don't feel constrained because the AP exam is kind of a very open, kind of open, and it's all about how well you can reason. So don't be afraid to kind of skip around as long as you get everything done. All right, so that's it. Thanks for everyone who stopped by. Remember to follow us at ThinkFiveable on Twitter and Facebook and Instagram, so you can see some of the things that are happening with us. Also, I believe we've got YouTube. No, we don't have Facebook, what I said. So follow us on Twitter and Instagram and YouTube, so you can get updates of what we're doing. And remember, because you're here, that's great. That means you already really care. So thanks for stopping by, and I'll see you around.